From now, I will start introducing my research. Psychoacoustic roughness is a subjective value that expresses the sense of roughness of sound and is one of the sound quality evaluation indices along with loudness, sharpness, and fluctuation of strength. Roughness unit ASPA is defined as the sensation produced by 100% amplitude modulated 1 kHz tone at a modulation frequency of 70 Hz at 60 dB. From now, I will play two audio. The first is AM tone at modulation frequency is 20 Hz. And second is same tone change modulation frequency to 70 Hz. The first one is 0.23 ASPA and the second one is 1 ASPA. Previous research has proposed a method to calculate roughness. However, various acoustic features such as phase and sound pressure level are shown to affect roughness, so this method do not be able to account for all of them, so I propose that machine learning can be used to develop a highly accurate model that can capture the relationship between these acoustic features and roughness. We have tried two machine learning architecture. The first is convolutional neural network. And the second is recursive neural network. I tried RNNs that include an architecture called bidirectional long short-term memory. For the training, I need audio data as input and roughness data as the teacher data. For this, data obtained through subjective experiment were summarized from previous research. The figure shows the dependencies of modulation frequency and roughness in amplitude modulated tone. From this figure, the information necessary to create audio data, such as modulation frequency, sound pressure level, and the shape of stimuli, is summarized in the table. These data were then used to create the audio files. In this research, 6,015 files were created. Each audio file is 1 second length and sampled at 48 kHz. Here for the increase training data, each audio file was divided into 200 milliseconds length segments at 100 milliseconds intervals. Before training, all audio data is divided into 80% training data, 10% validation data, and 10% test data. This is results. First is result of the CNN. The figure shows the roughness of the AM tone as function of modulation frequency for different carrier frequencies. The solid black line are prediction. The wavy line connected circle are the subjective value, and the wavy line connected by crosses are the standardized model. It can be seen that our prediction model is able to predict roughness with higher accuracy than the standardized model, but accuracy drop at lower modulation frequency and some oscillations can be observed. I also obtained result for the roughness of AM and FM tone and unmodulated bandpass noise as a function of other acoustic features, and found that in most cases the prediction was more accurate than the standardized model. Next is RNN results. The figure shows the roughness of AM tone as a function of modulation frequency for different carrier frequencies. In all cases, the prediction oscillates and we do not see much change in the prediction as the modulation frequency changes, and accuracy is also low. Similar to CNN, I also obtained result for the roughness of AM and FM tone and unmodulated bandpass noise as a function of other acoustic features. In some cases, highly accurate results were obtained, but large oscillations were observed and the accuracy was low compared to the standardized model and CNN model. This figure compares the root mean square error between the prediction and the subjective value of each model using test data. And this figure and the previous results show the machine learning model prediction are more accurate than the standardized model, and CNN can predict more accuracy than RNN model. As for RNN, oscillations were observed in many of predictions. This may be due to insufficient hyperparameter tuning. There is still potential for improvement in accuracy. As a conclusion, my research showed the usefulness of the machine learning approach to roughness prediction, and as a future work, tuning of optimal hyperparameter for RNN and try other architectures such as transformers and subjective experiment not only with test data but also with the complex sound such as engine and mechanical noise can be used to further evaluate generalization performance with confidence. That's all. Thank you for listening.